Bismillahirrahmanirrahim. Yes, hello everyone. This is Dr. Bassam Alhamad, Process Modeling and Simulation Chemical Engineering 324. Today we're going to be taking Lecture 9. We had taken a group of model equations, and these group of model equations that we have taken, we are going to work on taking some more examples of developing model equations for. So what we have taken so far, we have taken the CSTR example, and the CSTR example that we have taken, of course, the CSTR is a continuous stirred tank reactor, and the equations that we have developed for the CSTR reactor, if you just can recall that, it was dH by dt is equal to Fi minus alpha square root of h, and that was divided by area, as we can remember. And for the concentrations, we had dCA by dt is equal to Fi over V into CAI minus CA, which is the output, plus RA, and we said that it depends on the reaction, and you need to write the rate of reaction of RA. So these are the equations that we have obtained. And for the temperature, we said dt, the temperature changes in this format where dt over t is equal to Fi over V into Ti minus T plus Q over rho VCP. And of course, Q is the term for the heat transfer, and we have developed that. So these were the equations that we have developed for our system for the CSTR. Talking about the other system, we have taken a mixture, and within the mixer, and the thing that we said the difference is that this has no reaction, and for the mixer we have developed the equations, and the equations that we have developed dH by dt was similar. It was not different at all, and it was something that looked like that. But talking about the reactions itself, talking about the mixing process itself, the equation that we had obtained was the exit Y3, or we said dXA3 because it's liquid, over dt is equal to W1 over M into XA1 minus XA3 plus W2 over M into XA2 minus XA3. Okay, great. So just let me write that, the XA3, great. So these were the two systems we have taken, and then we have taken a third system. And the third system we have taken was for the surge tanks. Well, we said that we had a surge tank which looked like that, and we have an input and output. And we have taken two cases for the surge tank. This is vessel 1. And we have taken the examples where temperature is constant, and not only, of course, volume is definitely constant. Temperature is constant, that means it's either given, it should be given, or it could be assumed, depending on the parameters of the equation. Volume is constant, and of course, R is constant. And then we have developed our equations, and the equations that we have obtained was dP, I'll write that in white. It was dP by dt is equal to RT over V into Qi minus Q, and then we had an equation for Qi and Q, and we had obtained an equation then for the composition, which is the vapor composition, which was equal to RT over PV and that was multiplied by Qi into Yai minus Ya. Great. So these were the equations that we have obtained so far. So now, with examples that we have obtained here, we want to take some more examples that look similar to what we had taken before, except that they are a little different in a sense of attaching two different units together. And the first example that we are going to take here and have a look at is the conical tank, which looks like a cone. So it's a tank which is in the shape of a cone, and this tank which is in the shape of a cone, it is used in many different systems, and the idea which is different here, from the normal tank is that in a normal tank, what do we have? We do have the area is constant. So as we go up with the level, we can see that the radius is not changing, or the area is not changing as the height is changing. Whereas if you look at here, if the height is here, the radius is from this point to that point. Whereas if the height is here, the radius is from this point. Well, it's not the radius, I mean the diameter. So what I'm trying to say is that the radius is becoming different, and actually it's increasing. It's increasing every time when the level is increasing, which means that here the area is different. The area is different, which is different from the case of a normal tank. So if the question here in this problem, it's asking us to find out how does the height change with time. And actually this is one of the most important parameters that we need to measure here. How does height change with time? Beautiful. So what do we start with? We start with our normal equation, and that equation that we are going to work on is the overall mass balance to get the dH by dt, as you can recall. So the equation is, let me write this in white. So dm by dt is equal to the mass flow rate in minus the mass flow rate out, and that is rho. Okay, I cannot take area outside. Okay, did you recognize that? I was trying to take the area outside, but I think so I'm stuck because the area is also changing with time. And that is equal to rho n fn minus rho f, as we consider that rho is constant, so we can cancel out the rho from these terms. And what we are left with? We are left with this equation. However, now the challenge is here. So we have a dah dt is equal to fi minus f. And if we look at the area, the area is a bit challenging. And the area into height, this equation, or let me say the volume. What is the volume? What is the volume of a cone? The volume of the cone is pi r square, pi over 3 r square h. So that is the volume of the cone. And I know that that the radius is changing with time, and as well the height is also changing with time. And if we do substitute this is the volume, and this is actually dv by dt, right? This is dv by dt. This is dv by dt that we have here. So this equation will be d pi r square. Again, I'm trying to write in white. So it will be d pi r square h, beautiful, divided by 3, by dt, and that is divided by 3 out there, is equal to fi minus f. Okay, beautiful. Well, you can see there are two terms here, r and h, and it's not easy to do this calculation. It will be a bit complicated. It will be easier if you can substitute something instead of r as a function of h, and so we will have only h here. And that is the challenge that we have here. And we can do this similarly, simply by considering that what do we have? We have two triangles that are similar. So you have the big triangle and the small triangle. So talking about, well, the big triangle actually is here till it becomes full. Why? Because we are talking about a constant height that we already know, and a constant radius that we already know, that's the capital R, and of course the varying radius, the small r, and the varying h, which is a small h. And if you consider like this, the two triangles are equal to each other, this will be r over r is equal to h over h, and we can substitute r by that equation here. And talking about more details, if we have r square, this will be like r square, h square, r square, or the capital H square. And what we need to do, we are going to take the derivative of dr square, and we are going to do that a bit in a moment. But let's substitute r square, which is h square, r square. Let me do it here at once. So r square into h is h cubed into r square over h square. So we have our equation. We do have our equation will be 1 over 3 d pi, let me take pi outside, is constant. So we will have here h cubed into r square over h square. Even this thing is constant and we can't take it out. By dt is equal to fi minus f. Now we are just going to take the derivative of the h here, and this will be like an implicit derivative, where it is the derivative of h cubed is 3h square into dh by dt, and we take r square h square out of this term. So this will be, just to have some more space, r square over h square into dh by dt, So we have now our equation in f, which is alpha square root of h, an equation that has only the h by dt term appearing by itself. Beautiful, we got it at last. So our final equation will be something like, that. dh by dt is equal to fi, and if you just multiply it by the term here, well, this term is a bit complicated if you can look at it, but we have some terms that we can cancel each other. So like 3 goes with 3, and so yeah, this will be h square. It will be h square over r square, and h square, the small h square, which is h to the power minus 2, and this is divided by pi, and so this is divided by pi, and so this is the term that we have just multiplied, and it's multiplied by fi. I'll take fi outside, and that will be something like that, and this is multiplied by fi minus alpha square root of h, and of course we can multiply this by the whole term. So what do we have? We got our equation of dh by dt, and that was the aim of the problem here. So the whole idea of this problem is how to work on the conical, how to work on the modeling the conical tank. So that is example 1 for the conical tank. That is the example for the conical tank. I hope that you have got the idea for the con tank. And the next example we are going to take another example of working on 2 tanks on series. So hopefully we are done here, and we're going to see you in lecture 10. Thank you very much, and see you soon.